Welcome. My name is Larry White. I'm the UIL State Number Sense Contest Director and the UIL State Mathematics Contest Director. This is the third session of the 4 SAC sessions that have been scheduled to be done in replacement of the SAC sessions, SAC conferences. The fourth session will be on November 4th, and it will be for coaches only. And it supposedly is going to be live where the coaches can ask me questions and we can carry on dialogue. But for now, this is the third session, and I did not receive enough questions on the SAC tests. So instead of doing a second session with no questions, I decided I would do a special session on basis, since that seems to be a weak spot or a spot that many people do not understand very well. So we're going to do it on basis, and hope you enjoy. First off, before we get started, what happened to last year's regional state number sense and mathematics contest? We were given the option to release them last year for everybody to have, or to keep them and reuse them. I chose to reuse the regional state math and number sense test because the questions were good and I really felt like the kids needed to see them in competition. So I chose to keep them. You will see nearly all of the questions in both math and number sense throughout the year on my invitational meets and TMSEA contests. So you didn't lose them. They're all there and you're going to get a chance to answer them. Okay, let's move on. I want to talk a little bit about base systems. Lots of people have a little bit trouble with the base system, so it's a little bit of an introduction. Our number system that we use is the base 10 system, sometimes referred to as the Regrouping numeral system. We have 10 digits, 0 through 9. And we do all the things that we do in math class through the base 10 system. A couple of other interesting systems that you might want to do some research and look at. One is the Mayan numeral system. It was a base 20 system. It has 3 symbols, a funny looking football thing which represents 0, a dot, which is an individual unit, 1 unit, and then the horizontal line, which deals in units of 5. Interesting language. Number system. Babylonian number system is base 60. It only has 2 symbols. You can see them there. It's rather an interesting number system using base 60. There is no 0 in Babylonian numerals. We're all familiar with the Roman numerals. It's not really a base system, but it has 7 symbols, and then the bar to multiply the m's if need be. There's a special tribe of people in Africa called the Fulani tribe, and there's a village in the Fulani tribe that still uses base 5 today in their world. It's an interesting study if you want your young people to do some research. Take a look at the Fulani tribe. It's really quite an interesting group and interesting culture that they work in. The bases are based on their system and place value. As we know, base 10 has the ones place, or 10 to the 0, the tens place, or 10 to the 1, the hundreds place, 10 to the second power, the thousands place, 10 to the third power, so on. And it goes the opposite direction. The 1/10th place is 10 to the negative 1, 100th place is 10 to the negative 2, 1000th place is 10 to the negative 3. And it continues going well. Well, no matter which base you choose, I chose base 5 next, it's exactly the same thing as base 10, except you have the ones place and the fives place and the 25s place and the 125s place. So on that direction, likewise going the opposite direction in fractions or decimals. Base 2, same thing as base 5 and base 10. Ones place, twos, fours place, eighths place, and likewise the 1/2 place, the 1/4 place, and the 1/8 place. And then I'll put down base 3 as well. But if you notice that all the powers of each of the bases, the ones place is always the base to the power 0, which of course gives us 1. And then from the left, going to the left and then going to the right, it's symmetrical no matter what base you choose. So if I choose base 8 to look at, then base 8, I'm actually going to be looking at 1s and 8s and 64s and 2/16, and likewise going the other way, 1/8, 1 over 64, 1 over, I'm sorry, I said 2/16. No, how about 5/12? Got to be a multiple of 8, and then 1 over 5/12. So nothing changes no matter which base you choose. They all turn out exactly having the same type of place values. And there's base 16 and base 32 and base 64. And I listed these 4 intentionally along with this one here and this one and this one and this one and this one. I listed them because of their importance. I've heard people say, why do we need these things? Why do we even need to study them? If you really sit down and think about what our world is made up of, it's a very technological world without bases, without the bit system, base 2, zeros and ones, and base 8 and base 16 and base 32. These are all bit systems. And if without those, we don't have the technology that you're looking at right now, the iPads or the telephones or the rocket ships, whatever it may be, our technology is based on bit systems and different bases using the bit system. So why do we need these? Well, take it away and see what you have left. It's a good thing to have these things. So let's look at what's going on with bases. You can see in the example I have 1, 2, 3 base 10. That is pronounced 123. And the reason it is pronounced 123 is because it's 1 100, 2 10s, and 3 1s. And that's 100 plus 20 plus 3 is 123. But take a look over there to the right, over here in the 1, 2, 3 base 5. It is not pronounced 123. It is pronounced 1, 2, 3 base 5 because it is 125, 2 5s, 3 1s. It is not 100 or 3 10s or 2 10s or 3 1s. So it cannot be pronounced like that. So you have 125, you have 2 5s and 3 1s. Well, you can see that 125 plus 2 5s would be 10 plus 3 1s. So you have 25 plus 10 is 35, and 3 1s is 38. So 123 base 10 is 123. 1, 2, 3 base 5 is 38 in base 10. Now, that's how we expand them out using the powers of 10 or the powers of 5 in the nomenclature of place values. All right, let's look at these. So we have 1, 2, 3 base 8. That tells us that we have 1 8. I'm sorry, my apologies. We have 164 plus 2 8s plus 3 ones when you expand it out. So that's 64 plus 16 plus 3, which is 83 in base 10. I think you can see that. So if I did everything correctly, I tend to make little mathematical errors. So we have ones. I'm going to go through it on my mind one more time. I have 3 ones, 2 8s, and 164. That looks like it's 83. And if you look over at 1, 2, 3, base 3, you will see that that can't be because there are no 3s in base 3. The digits in base 3 only have 0, 1, and 2. So that cannot be a legal problem because there is no 3 in base 3. So I'm going to change that if you'll let me. Do 1, 2, 3, base 4. That'll be make it a little bit more sense. So we have 1 times 4 to the 3rd power, 2 times 4 to the 2nd power, and we have 3 times, I'm sorry again, I'm going to go back and redo. My apologies, my mind seems to be slipping here. We have 1 times 4 to the 2nd power, we have 2 times 4 to the 1st power, and 3 times 4 to the 0 power. And that will give us 16 and 8 and 3, which is, of course, 27. Anyway, that's how this works when you're playing around with going bases to base 10. Now let's go the other direction. Let's go base 10 to base x. It's an interesting thing because we use a division process to make this thing work easily in our heads, because you can do this in your mind by writing down remainders. If I take 83 and divide by 8, I get 10 with the remainder of 3, so I can write down the 3. Then I have 10 left over, so 10 divided by 8 is 1 with the remainder of 2, so I'll write down the 2. And then I have 1 left over divided by 8, which is 0 with the remainder of 1. So 83 is equivalent to 1, 2, 3 base 8. You can check that because that's 164, that's 2 8s, and that's 3 1s, and we already know that's going to be 83. Similarly, if we do it in base 3, we have 18 divided by 3 is 6, remainder 0, so we'll write that one down, remainder. And we have 6 divided by 3 equal to 2, remainder 0, so we'll put that one there. Then we have 2 divided by 3, which is 0, remainder 2, and so we'll put that one right there. And if you want to check that, you have 2 times 3 squared. You have 0 times 3, and you have 0 times 3 to the 0. And of course, that is 9. I'm sorry, 2 times 9, which is 18. Okay, so let's go over to the next one. We have 1, 2, 3, and we're going to change it to base 5. So if you take 1, 2, 3, and divide it by 5, you should get 2, 4 with the remainder of 3. Now we have 2, 4, and we'll divide that by 5, and we'll get 4 with the remainder of 4. And then we'll take 4 and divide that by 5, and we'll get 0 with the remainder of 4, if I did that correctly. And we can check that because it's 4 times 25, 4 times 5, and 3 times 1, which is 5 squared, 5 to the first and 5 to the 0. That should give us 123, and which it is. So using the little division and remainder technique is rather a neat way to be able to quickly change base 10 to a different base. So let's move on over. Let's talk about operations and base in different bases. First off, I'm not going to say you shouldn't use these words, but we tend to teach children in the younger years to borrow and carry. And it's one of the reasons why we have a lot of trouble with bases, is because we really don't understand what's going on with base 10, because we're carrying a 1 over, we're borrowing a 1. And in reality, you're really not. You're actually regrouping base 10s. So I tend to not like to use carry and borrow. I like to use regrouping, but I'll try to mention those words so that you know what I mean by regrouping. So let's look at this problem here. We have 5, 2 base 6 plus 1, 3 base 6 plus 4 base 6, and it should come out to be 1, 1, 3 base 6. Well, let's see how that works. Let's do the units digits. We'll take the 2, and then we'll take the 3, and then we'll take the 4. Oh, that got a little ugly, didn't it? Go back and do something a little different here. Take the 2, the 3, and the 4, and we'll add those up, and you should get 9, which is that right there. Okay. Now a 9 is actually a 6 and a 3. So what happens is we write down the 3 and we regroup, which means we rewrite the problem now by taking one of those 6s and bringing it over. So now we have the original 5 there, and the original 1 there, and the 1 there that we regrouped with. So we have, and then we have nothing left over in this area, on this last part. So we have 5 and 2 is 7. And there again, so 7 is a 6 and a 1. So we can put the 1 down, and then that just leaves us we have to carry over 1 6. So you bring the 1 over, and it gets added to the 0 because there's nothing left, and so you end up with 1. I'm gonna do that a little different now. 5, I'm gonna do it up and down because sometimes it can be seen a little better. Okay, we have 5, 2, 1, 3, and 4. So if you take and add this column right there, you get 9, and that's equal to a 6 plus a 3. We're going to take this 6 and we're going to bring 1 6 over here. So now we have 1, 5, and 1. So now we have 7, which is a 6 and a 1. So we're going to keep the 1 and we're going to bring this 1 over here. Let me get this out of our way. And we're going to put a 1 over up here. And so that's where it comes down and has the extra one. A little bit hard to see that, I guess, but I hope you can see that we're ending up with 7, 9, which there is no 7 and 9 in base 6. So this becomes a 6 and a 3, and this actually becomes a 6 and a 1. And so you end up with the 1, 1, 3 idea that we had over here. Okay. So that goes in. All right, let's try this one down here below. If you take the units digits, the 4 and the 2 and the 1, that should give us 7, but we're in base 5, so that's the same as a 5 plus 2. So we'll keep the 2 there, and we'll bring the 1 over to the 5 to the first place value. And so we have our 5 to the first place value is 0 and 3 and 4 plus the 1, 5 that we brought over. So now we have 8, and 8 is the same as a 5 and a 3. So we'll keep the 3. Then we're going to take that 5 and we're going to move it over to the 5 to the second power place, which happens to be all we have left there is right there. So we have a 1 there plus the 1 that was carried over. So we end up with a 2. And that's how that works. It's rather interesting. It's all a matter of just doing your sum, taking out how many of the bases you can take out, like in base 5, and leaving the remainder, and then just carrying through. Exactly like we would do in base 10, but we're just not using as many digits as we do in base 10. So let's go over here and play with this one. Let's look at subtraction. Once again, some people refer to this as borrowing. I like to refer to it as regrouping because that's actually what we're doing. We're regrouping it. You know, instead of going back here, instead of carrying a 1, I break the 9 into a 3 and a carry of a 6. The same thing over here. We're going to borrow, if you like that term. I'm going to regroup. So let's look at the ones digit. We have a 1 subtracting a 2. Well, we all know that really technically can't be done. So what we're going to do is we're going to regroup. We're going to take this 3 and make that a 2. And we're going to bring over a 4. If I can get it to right. We're going to bring over 4 because we didn't borrow 10 or a 1. We borrowed one of the 4s from the 3 4s we had. We brought over 1, and which is a 4. That's 4 1. So now this becomes a 5, and 5 take away 2 is 3. Okay. Now we're going to do the next value over. We have a 2 right there, and we have a 1 right there. So now we have 2 minus 1, and that is 1, which is it's supposed to be. Okay. Then we're going to take this 1 right here and this 3, and we're going to subtract them. But once again, we can't do that. So we're going to go over here to this 2, and we're going to leave that as 1 and bring over a 4. So when you do that, it's 5 take away 3 now becomes 2, and then we have our 1 left over, which gives us the 1, 2, 1, 3. That's how that works. And it's, when you get used to it, it goes pretty smooth as time goes on. Okay. Okay, I'm going to erase all that so I can try the one below it. So if you'll give me a second, I'll get rid of all that. There we go. Okay, so let's do this other one now. We have 3, oops, sorry. We have 3, 6, 5, 1, 7, 7. These are in base 8, okay? So we're going to subtract 5, take away 7, we cannot do, as we all know. So we're going to take one of them away from here, and we're going to take that, remember we're in base 8 now, so we're going to take that 1 8 and put it over here. That gives us 13. So 13 take away 7 is 6. We can't take 7 from 5, so we're going to take one of those 8s there. We're going to regroup it and move it back over here. So that's 13 take away 7 is 6. And then we can subtract and get that all in equally basic. So it's really an interesting concept. This is exactly what we do in base 10. For example, let me show you one real quick. How about 2, 3, 4, and take away, well, let's do 56. Now I'll erase that. I'll get rid of that one. Okay. Now, what? In base 10, 4 won't take away 6, so we put a 2 here, and we always put that little 1 up there, and that's not really true. What you're actually doing is you're regrouping. When you took that 1 from the 10th place, you're regrouping it, and that's a plus 10. That's how come it becomes 14 take away 6 is 8. Likewise, you can't take 5 from 2, so we take 1 from here, and we're not adding a 1 over there, we're actually adding a 10. 10 take away 5 is 5 and a 1. If we were taught to do base 10 correctly by regrouping instead of just putting little tick marks, we actually would understand base 6, other bases much easier than we are understanding them right now. So let's move on. Just a second, if you would, please. Okay, excuse me, I was just checking something. Okay, let's go play with multiplication. Okay, I'm going to do this long way so that we can sort of see what's going on. 4 times 0 is 0. That's not a problem. 4 times 1 is 4. That's not a problem. 4 times 3 is a 12. But you can't have a 12. So that's 2 5s. And let's see how I want to write that. Oh, shoot, I'm sorry. 12. We're going to rewrite that as a 10 plus 2. And so we can keep the 2, and we're going to take the 10, and we're going to bring over here 2 5s, because a 10 is a 5 plus 5. So we're going to bring the 2 5s over here. Now 2 times 4 is 8, and 2 is 10, which is written as 2 5s, 0 1s. So you can see we end up with 2 0, 2 4 0, which is what we had right there. So it worked out really nice. It's just a matter of regrouping when you get answers. Okay, we'll do this one here. 2, 1, 3, 5 times 3 in base 7. Okay, 3 times 5 is 15, which is 7 plus 7 plus 1, which means we're going to bring these 2 7s over here. 3 times 3 is 9, and 2 is 11, which is a 7 and a, I'm sorry, yeah, 7 and a 4. So we're going to keep the 4. We're going to keep the 1. We're going to keep the 4. We're going to bring the 7 over here. 3 times 1 is 3, and 1 is 4. And then 3 times 2 is 6. So we have a 6 and a 4 and a 4 and a 1. And that's how that multiplication works. It's relatively fast. It's not quite as fast as double digits. You have to be a little bit careful about double digits because it works. Things move around a little bit different. It's not quite as smooth as it would. The only double digit one that works really nicely is when you're multiplying by 1, 1. And the 11s trick you use in base 10 works really nicely, as the 1, 1 will work in other bases. But that's another story one day. If you're interested in that, just give me a holler and try to share that with you. Okay, we can divide now and see how that goes. So let's, I'm going to make this a little bit bigger so we can see what's going on. So 3 goes into 1 0 times. So multiply by 3 is 0. When you subtract, you have a 1, and you bring down the next group. Well, you're not bringing down a 2. You're bringing down a 2 6s. So you're actually bringing down a 12, which when you add that together is 13. 3 goes into 13 4 times, which is 12. And when you subtract that, you have 1, and you bring down the next group. But you're not bringing down you're not bringing down a 3. You're bringing down 3 6s, which is 18. I thought I had this fixed to where it would come out even, but it doesn't. It's 19. So you have 19, and when you divide that by 3, it gets 6, and that's 18. We're going to end up with a remainder of 1. I didn't want to have a remainder of 1, so I'm going to go ahead and stop there because I thought I had a nice even number, and I did not. So it should be 46, and you'll have 1 left over. So it's going to be a decimal come into play there. You might be tempted to say, I'll take that remainder of 1 and put it over the 3. That works sometimes in bases. It doesn't work all the time. So you might want to be a little bit cautious about that, whether it works like that. I didn't mean for it to be uneven, but it did. So it is what it is. Okay, let's do the other one. We have 2, and we're in base 3 now. So we have 2, 1, 2, 1. These are all in base 3. Notice I don't really need to have to put the 3 there because 2 in base 3 is the same as 2 in every base except, well, every base, I guess. Yeah. So we'll divide. 2 goes into 2 once. That's 2. We subtract. We get 0. We bring down the next one, but it's not a 1, it's a 3 that we're bringing down. So 2 into 3 is 1, that's 2. We'll subtract that, gives us 1. We'll bring down 2 3s, which is a 6, and this becomes 7 now. 2 into 7 is 3, and that gives us a 6. And we'll subtract that as 1, and we'll bring down another, oops, I'm going to run out of room here. We're going to bring down another 3, which is 4, and 2 goes into 4 2 times. You just have to remember when you're subtracting, when you're dividing, you're bringing down the next group, and it's not the next number. It works real good in base 10 because the next group is a 10. But in bases, that next group happens to be that base. And this is the one that's the most difficult for people to understand and see. You're bringing down the next group, not the next number. Okay, as it turns out, just about anything you can do in base 10, you can do in any other base. Square roots, changing to decimals, changing to fractions, converting base 2 to base 4 to base 8 and vice versa is a really nice, neat little trick. Converting base 3 to base 9 to base 27 is interesting, 4 to 16 and so on. There are lots and lots of different things you can do with bases, because if you can do it in base 10, you can do it in any base. Let me show you real quick. This is pretty interesting. I'm just going to make up a base 2 number. That's base 2. And if I want to change that to base 4, you realize that 2 squared is base 4. So it takes 2 bits to make a base 4. So we can take those 2, that's 1. We can take those 2 and see, that's a 2 and a 1, so that's 3. We can take those 2, that's a 1, and we can take that one, and that's a 1, and that's what it looks like in base 4. Because I have 1, 1, no 2s. I have 1, 1, 1, 2, 1, 1, no 2s, and 1, 1. In base 8, I can take 3 at a time because 2 to the third is 8. So I have 1, 1, no 2s, 1, 4, so I have 5. Here I can take 3 of them, and I have 1, 1, 1, 2, no 4s, so I have 3, and then this is all that's left, and so I have that, and that's in base 8. That's a really nice, fun thing you can do. You can do that with 2s, 4s, and 8s. You can do it with 3s, 9s, and 27s, and 4s and 16s, because they are powers of each other, and that's what makes that work. Now, somewhere along the line, bases get larger than 10. For example, base 11. Well, you can't put a digit 10 in base 11, and so on. So they have to have a different terminology. So they use letters as symbols. A refers to the digit 10, B refers to the digit 11, C to the digit 12, and so on. Base 16 has A, B, C, D, E, and F. A for 10, B 11, C for 12, D for 13, E for 14, F for 15, because base 16 has digits from 0 to 15, but you can't put double digits in a single spot. So we use letters A, B, C, and so on along the line. All right, my friends, I hope that helps some of you that have been struggling a little bit with bases. Maybe it'll cause you to have some more questions about bases, and that you can email me, and coaches and teachers, you can email me and get clarifications on some of this stuff, or anything you want to get clarified with bases. Please remind your students not to email me. I can't accept emails from students, but I will be more than happy to help you with any of the base problems that there are. There are numerous basic problems on the number sense and the mathematics contest. I think it's an important concept that we need to pay particular attention to. With that, I tell you guys, stay safe. Good luck at working through school this year and through competitions. Work hard, play fair, and I'm getting ready to go off on another tangent somewhere. Have a great day. Thank you for attending.